Hello everyone, for this last circuit what we are going to do is look at power. What is the watts of this circuit based on the parameters that we've already established and as we've worked through this circuit, and how we can look at the relationship of power between each component and the total as well. So there's some different ways that we can look at power. We can look at the amount of energy times the force that's being applied, different things like that. That all has to do with the concept of power. So if we look right at the source, one of the things that I like to do when I am looking at the source, what is the power that exists? What is the power that is being consumed when I have a relationship to the source? So we can do the power is equal to the total current times the applied electromotive force. So the quantity of electrons and the force that's being applied, it takes energy to move those electrons through that circuit, and I have to overcome the opposition. That's what's determining how much power is being utilized. So my total current in this circuit was 4 amps. The voltage is 120 volts. So I know my watts of my circuit will be 480 watts. So another way that we can look at the power, and we'll look at just this component now, is based on that current value and the energy that it's being used to move those electrons to the circuit. And at this one component, how much energy is it using when I am forcing 4 amps through that resistor, and it has to overcome that opposition. That's also an expression of power. So we can look that based on the quantity of electrons, or the current squared times the opposition that it's holding up. How much energy does it take to move those electrons through the circuit? And we can look at that as a wattage. How much heat is this being dissipated? That's another way to look at this. So when I look at that, I know based on 4 amps squared times my 10 ohms, for this I would have 160 watts would exist at that component. If I go down here, all of these relationships, what you're going to see in a series circuit, if we looked at the voltage drops, we can also look at the relationships of power in a series circuit based on this being a 5 ohm resistor and this being a 10 ohm resistor. So if this is 160 watts, let's just do the relationship. Okay, so if I know that this is 160 watts, and I look at this 10 ohms of opposition and this 5 ohms of opposition, based on that value, okay, I know that this is half the opposition. So is it going to allow for more energy to be utilized at this point, or is it going to require less energy? Is there going to be more heat dissipated? Is there going to be less heat dissipated? Okay, so I know at that point, based on the parameters of this being a 5 ohm resistor, there still being 4 amps, okay, this is going to be 80 watts at this point. And we look at the relationship. Was the opposition half? So the energy is half. I go over to here, and one of the last things, all of that energy, law of conservation of energy, all of the energy that exists in this circuit, what is ever at the source, has to exist within this circuit. So if I look at my power total, it will equal the power at the first component plus the power at the second component plus the power at the third component. Very similar to Kirchhoff's voltage law. What was Kirchhoff's voltage law about? The conservation of energy. What is power about? The conservation of energy. The energy that is put into the circuit has to be coming out of the circuit. And it doesn't matter, even if we took the losses of all of this, it has to be true. You can't create energy, you can't destroy it. It all has to exist within some component of this circuit. So if I had 480 watts and I could transpose 480 minus 160 minus 80, I'm going to look at this as being 240 watts of heat energy, however you want to visualize, at that point in my circuit. So I hope this has helped to take us through each and individual step, how to calculate some of the components within a series circuit. See you in the next one.